Okay, students, this is our Unit 6 Part 1 review video. It's all about probability in Unit 6, and this will cover 6.02, 6.03, 6.04, and 6.06. Okay, some information to save. So I like to do these with my class. These are the definitions and the important formulas and things like that that you need. So you could take a snip of this or a screenshot and save it in your notes if you're keeping track of notes somewhere. Definitions. In the study of counting and probability, an experiment is any process that results in one or more results, which are called outcomes. And so I think a lot of times about this in science. So we have an experiment in science, and then we have these things that are called outcomes. Okay. We have tree diagrams that help us to use the addition and multiplication principles, and it's all about counting possible outcomes. So we use tree diagrams to find what the possible outcomes are. We use these things called counting principles to find out how many possible outcomes there are. So if you want to know what they are, you use a tree diagram, and that will give you the specific outcomes. If you want to know just how many there are, then you can use counting principles. There's the addition counting principle, and I teach my students that a key word here is the word or. So if it says what is the probability of, or how many outcomes if I have this or this, okay, so you're putting them together by addition. Okay, so this is addition when you see or. You don't always have to see the word or though, and we're going to talk about an example here in a second with that. Multiplication counting principle is when you multiply them, and this is when you see the word and. So it's this and this happening. So flipping a coin and rolling a dice. So your possibilities are multiplied together instead of added. So this is multiplication. All right, and then the final definition down here for 6.02 is a factorial. And we use factorials to help us find counting principles or total outcomes. But a factorial is represented by this right here, where you see n is the number, and then that exclamation point means factorial. So what that really means is that you're taking the number n. So let's say if it was 5 factorial. Oh, why did I use the number 5? It's hard to write. 5 factorial, you take the number 5 and you times it by 1 less, and you continue down that pattern until you've hit the number 1. So 5 times 4 times 3 times 2 times 1. And the answer to that would be what 5 factorial equals. Okay, and we have this special situation, 0 factorial will always equal 1. All right, so I can use addition and multiplication counting principles to solve problems. So here's my situation. A breakfast special includes an entree, which can be pancakes, waffles, French toast, omelet, or country scramble, a meat, which is sausage or bacon, and a beverage, coffee, tea, juice, or soda. How many different breakfast specials are possible? So we just want to know the total outcomes, okay? So I'm going to go ahead and use my addition or my multiplication counting principle here, because it says and. So I'm getting all of these together, not one or the other, okay? So first of all, I count how many entrees do I have. So I look at the entrees. Well, I have pancakes 1, waffles 2, French toast 3, omelet 4, country scramble 5. So I have 5 choices for the entree. Okay, so there's my entree. Times, I have how many choices for the meat. So the meat would be sausage or bacon. So I have 2 choices for the meat. And then the beverage, I have coffee, tea, juice, or soda. So that is 4 choices. So now that I have all my possible choices here, I multiply them together to get my total. 5 times 2 is 10. 10 times 4 is 40. And so my answer to this question would be 40 possible different breakfast specials. Okay, so let's look at a factorial now. If I'm looking at this and I say, okay, well, I want to know 8 factorial. 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 and times 1. And then you go ahead and calculate that. I'm going to grab my calculator real fast. Okay, so now that I have my calculator, we do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that gives us this big number of 40320. Now, if you're noticing on your calculator, my calculator actually has a factorial button. It'll be the exclamation point, so you could just click 8 and then that factorial button. If you're using Desmos calculator, which is what I suggest my students do, then there's a factorial button there as well. I think you have to hit 8, and then in the middle there's the word function. You click that, and then the factorial sign's there. And if you type it in, it should give you the same answer, okay? But if you don't have a calculator with a factorial button, you can easily just multiply it out like we did here. All right, so 6 is going to be the same thing. 6 times 5 times 4 times 3 times 2 times 1. And then once again, you can just type that in to your calculator, or you can go 6 times 5 times 4 times 3 times 2 times 1. And, oh, I put times 0 instead. So 6 times 5 times 4 times 3 times 2 times 1. And you get 720. Now, before I go to that last question there, what would happen if you had a question that said maybe 8 factorial minus 6 factorial? So we've already found both of these, and this is what I would suggest doing on questions like this. Take whatever factorials they give you, find those first, and then perform the operation in between. So this would be the 4030 or 320, and we would subtract 720 from it. Okay, so we would take our 40320 and subtract 720, and so 8 factorial minus 6 factorial is 39600. So 39,600. Okay. Now, this one right here is telling us to find 3 factorial times 5 factorial. So if there's nothing in between there, you multiply them. So first I'm going to find 3 factorial. Okay. First I'm going to find 3 factorial. Then I'm going to find 5 factorial. And then I'm going to put them together by multiplication. Okay. So 3 factorial is 3 times 2 times 1. And that's 6. Oh, duh. 3 times 2 is 6. Oh, my goodness. That was crazy. 5 times 4 times 3 times 2 times 1. So 5 times 4 times 3 times 2. See how Mrs. Guyman relied on that calculator and she didn't need it for that first one? My goodness, that was kind of silly. But okay. So now we do 6 times 120. And so 6 times 120 is 720. And that is our answer for 3 factorial, 5 factorial. All right, let's move on to 6.03. So here's our information to save page. We have a definition called a sample space. This is the set of all possible outcomes of an experiment. So the sample space is not just how many outcomes there are, it's what they are, okay? The definition of an event, we talked about that, what that was. It was the we talked about outcome. An event is a subset, which is, for example, rolling a dice. That's an event. That's something you're performing on the object. A simple event is just one of those. A compound event is multiple of those. So maybe rolling a dice and flipping a coin. Or maybe it's flipping a coin twice. Or maybe rolling a dice 4 times. Okay. The probability of an event is the measure or likelihood that the event will occur. A lot of times we write these as percents. Most of the time we write them as percents actually, but they can be written as fractions and decimals. So here's how we find the probability of an event. We take the total number of outcomes of the event. So, for example, if we're talking about flipping a coin, what are my probability of getting heads? Okay, well, first of all, the total number of sides on a coin or total number of possibilities on a coin are 2. There's only 2 sides on a coin. Okay, the probability of getting heads is 1 because there's only 1 heads on a coin, unless it's a double-headed coin, and then it's not really a coin, right? So the answer would be 1/2. Or we could change that to a decimal, which is 0.5, which is then 50%. Okay, so this is the things that you're going to be doing when you're finding probability. And if you have questions about these definitions, you'll have to ask your teacher. But I would suggest taking a snip or a screenshot of this. All right, so some things that we did in this section. There are 2 small sweaters, 2 medium sweaters, and 1 large sweater in a bag. What is the probability that Lydia randomly pulls a medium sweater out of the bag? Okay, and we're going to write the probability as a %. So first of all, I always start with my total. Okay, I love to start with my total because that's just a good starting spot. The total always goes on the bottom. I'm trying to write the word total here, but my pen is not wanting to make those circles for some reason. Okay, so total always goes on the bottom. That's the total number of items. Well, we have 2 small, 2 medium, and 1 large. That makes 5 sweaters in the back. Okay, that's the total. Medium is how many mediums do I have? Well, I have 2 options for medium, so that's the top. So I have a 2/5 chance, which if I change that to a decimal, 2 divided by 5 is, oh goodness, 2 divided by 5 is 0.4. And then changing that to a decimal or a percent would be 2 places. So I would make it a 0 there, and it would be 40%. And it's asking for it as a percent, so I would write that as my answer. Okay, moving right along. The months of the year are written on cards and dropped into a box. Remington selects a card without looking. What is the probability that Remington selects a month that begins with the letter M? Okay, so first of all, the total number of cards in the bag. Well, there are 12 months in the year, so there have to be 12 cards. How many of those begin with M? So let's see. January, February, March, April, May, June, July, August, September, October, November, December. Oh, looks like there's just 2 that start with M. So that would be 2 out of 12, which I like to reduce it. That's really 1/6, which if we change that to a decimal then, we would do 1 divided by 6. So we get 0.16, and it just continues on because it's repeating. Okay, so this right here says we want a decimal to the nearest hundredth. So because this is 6 forever, we can say that this is 5 or more, so it rounds the one in front of it to a 7. So this would be 0.17, and that is how you would answer on your assignment. Rounded to the nearest hundredth. All right, 6.04. So this was the multiplication rules for probability. So this was now, we have compound events. We're taking more than one event. So now we're flipping a coin and rolling dice, or we're picking a shirt out of a bag and a pair of pants, okay? And so we're doing more than one. We're doing 2 events. So for events A and B, where A occurs before B, okay? So if it has replacement, and it will tell you that they're going to replace it, or it'll be something like, I take the cookie out and I eat it. Well, obviously he's not going to put the cookie back in if he's eating it, okay? So that would be without replacement. Okay, so it'll tell you either it's replacing or it's without replacement. So if it's with replacement, then we basically just multiply the 2 events, multiply the 2 probabilities. Okay, so we're going to have 1 fraction times 1 fraction. Okay, if it's without replacement, we have to take the first fraction, so the first probability, and we have to times it by the second probability, meaning we're going to deduct the number of items that we take out. So let's kind of move on, and we're going to see some examples here. So notation here, P and then in parentheses B after A means the probability when event B follows event A. Okay, another tip, from now on when a problem says without replacement, assume that means that the result of the first step is not known. Okay, all right, So review probability with and without replacement. So here's a magician, and he's performing for an audience of 32 men and 20 women. Okay. He selects a volunteer from the audience, has the volunteer stand behind a curtain. Okay, so right there, that's the clue. If the volunteer is standing behind the curtain, they're no longer available for the second pick. Okay, so now that's without replacement. So this would be without replacement on this one. And then selects another volunteer. What is the probability that both volunteers are men? Okay, so first of all, we have 32 men and 20 women. So total, we have 52 people to choose from, men and women together. Okay, so remember I said we're going to be multiplying these because you're doing two things. Now, the first one, we want men, so we have 32 men to choose from for the first volunteer, okay? Now, say we do get a man, okay, and they're going to stand behind the curtain. So now guess what? We only have 51 volunteers to choose from now because that one person is behind the curtain, and we only have 31 men to choose from because we're going to assume that the first one was a man, okay? So now this is how it works. We multiply straight across, okay, on top and bottom, and then we're going to change it to a percent. So I say 32 times 31 equals 992. And 52 times 51 equals 2652. Okay, so then we change this to a decimal, so 992 divided by 2652 would be 0.374, and I'm going to change it to a percent from here, so 1, 2, so 37.4%. So let's talk about what that means. So if it's a percent less than 50, then it's unlikely, mostly unlikely to happen, okay? If it's exactly 50%, then it's equally likely, and if it's more than 50%, then it's likely it's going to occur. Well, the probability of this guy picking 2 men in a row, okay, just randomly, would be 37.4%, which is more on the unlikely side, okay? Not impossible, because that would be 0%, but more unlikely that that's going to happen 2 in a row. All right, so here's another example. Joni and Chachi are friends. Each has a box that contains 3 raisin cookies and 5 lemon cookies. Okay, so automatically I'm thinking a total. I have 8 cookies. I'm going to use that somewhere, okay? Without looking, Joni takes a cookie from her box. This first cookie is lemon, so she puts it back. Oh, that's with replacement, okay? So now I'm thinking both of them are going to have a total of 8 on the bottom with a times sign in between. Okay. The second cookie is lemon as well. What is the probability of Joni's 2 lemon cookie outcomes? So we know what she pulled out, but we want to know what were her chances before she did that. Okay. So the first one was lemon. There are 5 lemon, so that's my probability for the first choice. Puts it back in. I still have 5 lemon out of 8 total. So now we have 25 over 64. I just knew that multiplication. And our percent then, if we change that to a decimal, we get 0.3906. So I would say that she has a 39% chance of this happening. Now, this is what really happened. So her chances weren't that hot, but that's what happened, and that's what probability is about. Probability is just the chance of it occurring. What really happens could be different, okay? But just the chance is probability. Okay, so now let's look at it with tree diagrams. And I'm putting this one on there because you have one like this on your quiz. So you're at the arcade and begin with 6 quarters and 4 tokens in your pocket. You randomly choose a quarter, use it in the machine, so we're not replacing it. And then we randomly choose another. So here we go. 6/10 represents the first choice, okay? 4/10 represents that you get a token. All right, so now what is the chance that I get a quarter 2 times in a row? Well, do you see how they subtracted 1 on the bottom here? It's only out of 9 now. That's because they're going to use that first coin in the machine. Let's say it's a quarter. Well, we already chose a quarter the first time, so we already put that 1 quarter in there. Now we only have 5 choices for the quarter. But guess what? We still have 4 choices for the tokens because we haven't used the token here. We used the quarter. Okay? Then down here, if we use say we're going to get the token first, well, the quarter, we still have 6 quarters in our pocket because we used the token first. But now we only have 3 tokens. Okay? And that would be your chances using a tree diagram. All right, last section here, 6.06. Here's your information to save page. 6.06 is very similar to 6.04, with and without replacement. But now we have these words called independent and dependent. Independent means that it's not going to depend on what happens in the first one. Okay, so this would be with replacement, you can think of it as. Okay, so you're going to put it back in, or it doesn't matter. Like, for example, if I'm flipping a coin and rolling a dice, what I get on the coin is not going to matter what happens to the dice. They're completely different objects. Okay, dependent means that the first event's what happens in the first event is going to depend on what happens the second event. So I would say that this one was without. And usually on these ones they're going to say without, or like on the last question it said that we ate, or not the last question, the one with the magician, it said that they stood behind the curtain. Okay, all right, so the next big thing I want to go to is this right here, very similar to what we just saw. This is called conditional probability. Basically it's saying B given A has already happened. So that's where we're going to end up subtracting things like we did on without replacement. Okay, so I'm going to give green checks and red X's here. So flipping a coin multiple times, we're just determining if these are independent or dependent. Flipping a coin multiple times, okay, well, to me that's a green check. It's independent. It doesn't matter. I'm going to flip the same coin again and again and again. It's not like I'm going to cut half of the coin off and now not have one of the sides. Okay, that would be silly. Rolling a number cube multiple times, still independent. Nothing's changed on the cube, number cube, which is also a dice. Okay, picking cards from a deck without replacement. Oh, there's our word without replacement. So now it's going to affect what's going to happen the second time because now I've taken one less card out. Okay, picking marbles out of a bag with replacement. Well, if I'm going to put it back in, it's not going to affect what happens the second time. Okay, so here's a practice. I can find probability of independent events. And then I gave you the hint here, it's with replacement. So this one says that a spinner numbered 1 through 5 is spun 3 times. Okay, so I'm going to have 3 probabilities because it says it's spun 3 times. And that's where I like to start. I like to start setting up the fractions. I know I'm multiplying in between because that's what probability is when you're finding dependent and independent events. So what is the probability of spinning number less than 3? Okay, so now I have to think. How many numbers are less than 3? Oh, first of all, there's numbers 1 through 5. So I have 5 choices here. 5 here because it's not affecting it, right? Doesn't matter. I'm not cutting part of the spinner off, okay? So there's, let's see, numbers 1, 2, and 3. Oh, but we can't use 3 because it's numbers less than 3, so 1 and 2. So I have 2 choices here. A number greater than 3, okay, so that means I have, can't count 3, but I have 4 and 5, so that's 2 more choices. And a number exactly 3, so there's only one of those, so I would put not 3, ooh, I almost put 3, I would put 1. Now we multiply straight across, so 2 times 2 is 4, times 1 is still 4. Not adding, multiplying. 5 times 5 is 25. Ooh, 25. What's 25 times 5? I think that's 125, but I better double check. Yep, 125. Okay, so now it wants it as a decimal. So we're going to take 4 and divide 125. And the decimal is 0.032. And that would be our answer because it wants it as a decimal. Now, if it said a percent, that would be 3.2%, which that's very unlikely that it's going to happen, right? Yeah, almost impossible. Not, though, because it's still 3.2. Okay, so this one is a dependent event now, so this means without replacement, so watch what happens. We have a bag containing 4 green, 4 red, and 2 blue crayons. Okay, so right now I'm thinking I'm going to have a total of 4, 8, 10 crayons, right? Okay, so what is the probability randomly choosing 2 crayons? Oh, here's my second probability, so I have to have 2 fractions. Without replacement. Okay, so this is kind of like the magician one. So I know that because I'm not going to replace the first crayon, I'm only going to have 9 options for the second probability, okay? And I want 2 red crayons. So the first choice, I have 4, okay, because I know that that's how many are in the bag. It says it right there. And for the second choice, I'm going to assume that I pulled that red one out and I'm going to leave it out. I'm going to put it on the counter. So now I only have 3 options. Then this would equal 12 over 90, and I want it written as a decimal to the nearest hundredth. So 12 divided by 90 would be 0.13, and then it's repeating. So I would say to the nearest hundredth, it would be 0.13. Now, what would happen if this said, instead of 2 red crayons, it said 1 red and 1 blue? Okay, so let me show you what that would look like real quick. So we're still doing 10 out of 10, okay? And we're still doing out of 9 because we're going to leave that crayon out, okay? This is still 4 because it's still, we're talking about the reds. But then, because it says 1 blue, I don't subtract 1 from the top. I just take the blues that are up there, and there says there's 2 of those. So that would be 8/90ths. And then we could find the decimal from there. Okay, I think that's it. If you have any questions about any of this information, I know it was a lot, please ask your teacher. Have a good one.